Okay, so I thought I'd do a video on the introduction to chemical reactions and balancing. There'll be some solubility rules in here as well. So now it really feels like we're doing chemistry. And so what you'll find is on the left-hand side of a chemical reaction, you do have your reactants. And then on the right side, you have your products. Okay. And so what happens is the bonds in the reactants are actually broken and new bonds are formed to make products. So you're not actually making anything new in per se that you're creating new elements. You're just rearranging them in a different way. And so we use various symbols in these chemical reactions. And so the plus symbol should look familiar. It's used to separate reactants or products. The arrow symbol is the yield symbol, and that'll separate reactants from products. Sometimes you'll see the equal sign. I prefer that you don't use this, but you might see it. This double-headed arrow, or I'll probably write it that way, is a reversible reaction. That means the reaction could go in both the forward and backwards directions. A little s would be a solid, little l is a liquid, little g is a gaseous compound. AQ means an aqueous compound, meaning it's something dissolved in water. Particularly, you'll see this with acids a lot of times because that is mixed with water. Or if you will find that something is soluble, it's going to be considered aqueous. A solid is going to be something that is insoluble. And so you'll need to pay attention to that the solid label goes when a compound is insoluble, and the aqueous label will be when something is soluble, meaning it's dissolved in water. Now, if you see a triangle over the yield symbol or the word heat, that means heat is added to the chemical reaction. And if you see a chemical symbol like platinum on top of an arrow, that means a catalyst is added to help that reaction occur. So if we're determining our labels, solid, liquid, gas, and aqueous, we're going to use something called the solubility rules. This is using your poly-ion sheet. And I'm going to do a separate video on this just to be safe. And so on the back of your poly-ion sheet, you will see the rules. And you always will go in order. So if the first rule works, then you're going to stop and label it. If the second rule works, then that's the one you're going to use. There is this general rule of thumb. So these ions, so the potassium, sodium, chlorine, nitrate, sulfate, and this IUM is for ammonia, this guy. If compounds have a combination of those ions, it's going to be soluble, meaning we are going to label it aqueous. So in general, if it's a solid precipitate or insoluble, you're going to put an S next to the compounds. If you look at the solubility rules, barium sulfate and silver chloride would be indeed insoluble, so they would be solid. If you have a chunk of metal, those are going to be solids. If you have a liquid, you're going to put an L in next to it. In general, that'll just be water, unless you're told differently. You might be told bromine liquid or mercury liquid, so you might possibly see those as well, or mercury liquid. Now, if it's a gas, this tends to be if it starts with a nonmetal. So if your compound starts with a nonmetal, most likely it will be a gas. Usually be ones that you've seen before: carbon monoxide, carbon dioxide. A lot of these we saw in the previous unit. Now your Hofbrinkels, these are molecules that are diatomic, so they like to bond to themselves. Now these tend to be gases as well. So I'm just rewriting it to show that they are diatomic, and they are never going to exist in a chemical reaction by themselves. You're not just going to have an H. It'll be an H2. Now, if it's soluble or aqueous, we're going to put an AQ next to it. That means it's been dissolved in water. And so I put some common ones: KNO3, NaCl, K2SO4. All of these actually, if you look at the solubility rules by rule number 1, said that these are soluble compounds and be labeled aqueous, and your acids and bases, particularly your strong ones, will be considered aqueous. So if we go through this practice, it would help you to determine the solubility rules. And so I'm actually just going to go through the answers to make sure you know how to do this. So if I look at this first one, carbon is a nonmetal, so I know this is a gas. I have Mg, that's a chunk of metal, so I'm going to put a solid. I have Br2, that's a Hofrinkel, so I'm going to put that that's a gas, but if you look at the periodic table, it's liquid at its natural state. I would be fine with either. If I look at barium sulfate, I'm going to look at my solubility rules. Rule number 6 is the one I'm looking at, that sulfates are soluble except for calcium and barium, and so that would be a solid. For chromium 3 sulfide, I don't see any rules about chromium, but I do see them for sulfides. This is rule number 5. And rule number 5 says carbonites, hydroxides, oxides, phosphates, silicates, and sulfides are insoluble. So I'm putting a solid. Rubidium bromide, Rb, is an alkali metal. So that's rule number 1. Alkali metals are going to be soluble. So aqueous. HNO3 is an acid. Starts with an H. Potassium phosphate. If I look at rule number 1, it says potassium containing compounds are soluble. Ooh, it's a nonmetal, so that makes that a gas. Calcium sulfate, let's look at this one. So I'm seeing if there's any rule that pertains to calcium or sulfate. I don't say anything about calcium, but I do see sulfates are soluble except for calcium and barium. So rule number 6 would make that a solid. Let's look at this next one, silver nitrate. So I'm going to see which rule comes first, silver or nitrate. And if I look, rule number 2 says nitrate containing compounds are soluble, so that would be aqueous. That actually comes before rule number 3, which is silver. Lead 2 sulfate, it says rule number 3, lead containing compounds are insoluble, so I'm going to make that a solid. Sodium acetate, rule number 1, sodium containing compounds are aqueous, and it starts with an H, that makes it an acid. So that is the correct answers for those practice problems. So now I'm going to teach you balancing reactions. And so balancing reactions, I'm going to teach you 2 techniques. One is the observational technique, and then one is an algebraic way when you just can't get it. So I'm going to come back to these rules. So we're going to place coefficients in front of a compound to balance. A reaction is balanced when you have the same number of each element on both sides of the reaction. So that's what we look for first. I always like to start with the most complicated or unique compound, and that tends to be the ones with lots of subscripts. Generally, you're going to balance hydrogen and oxygen last. Sometimes you can balance your polyions by keeping them together, and sometimes it makes water a HO because you can balance that O and H separate. And then we're going to look for 2,3 combos, and then this is a specific kind of reaction. So let's look at this. So if I look at this first reaction, I'm going to first see if it's balanced. And what jumps out at me is there's a 2 here and there's only 1 silver. So I know that reaction is not balanced. So that means I'm going to balance by placing coefficients in front to make them have the same number. So if I look at Ag2S, I have 2 Ag, so I'm going to put a 2 in front of the AgNO3. Now I have a total of 2 NO3 groups. So I'm going to place that now on the right side. That balances my NO3s. That now gives me 2 H's. Now if I go over here, I have 2 H's, 1 S, 1 S. So I'm done. So that's how you do it. You just go back and forth, making sure you have the same number on both sides. Okay, so let's look at this next one. Again, I like to start with the most complicated. I also notice that H and O are separate, so I'm going to rewrite water as a HO. And so let's start with the zinc phosphate. So I have 3 ZNs. So a 3 is going to go in front of my ZN. That now, this is 3 times 2. That's how we figure out how many OH groups there are. So this is multiplying. 3 times 2 is 6 OHs. So I go over here to the water. I'm going to put a 6 in front. Now that gives me 6 H's. But over on the left, I only have 3. So I'm going to put a 2 here. So 2 times 3 is 6. And if I distribute that 2, I'm going to have 2 PO4 groups. Over here on the right, I have 2 PO4 groups. So it's all balanced. So this is a water, making water a hoe example. Okay, the next example, I have the 2-3 combo. Notice I have a bunch of 3s and 2s. So I'm going to think the common denominator idea. And so common denominator with 3s and 2s would probably be a 6. So you could kind of start anywhere here. So if I put a 2 in front of FeCl3, that would give me 6 chlorines. So I'm going to put a 3 over here. That gives you 6 chlorines. So 3 calciums, 6 hydroxides. Put a 2 here, 6 hydroxide, 2 Fe's, 2 Fe's. So that was the 2-3 combo. If you see, it just saves you time. Okay, so if we're looking back at my rules, there's the difficult, the water is a hoe, 2-3 combo, and this is a special kind of reaction called a combustion. So you're going to have a bunch of C's and H's plus O2 always yielding CO2 and water. These tend to be the most complicated for balancing. So I always suggest starting with carbon first. So I have 3 carbon here. So I'm going to put 3 carbon on the right. Then I'm going to balance hydrogen second. So I have 8 on the left, so I'm going to put a 4 over here. That gives me 8 hydrogen on the right. And then what makes this tricky is we have oxygen in 2 places. So I have 3 times 2 is 6 from the CO2, plus 4 times 1. So a total of 10 oxygens on the right-hand side. And then I look over here, 10 divided by 2 would be 5. Now, if this doesn't work, let's say it's not divisible by 2, then you're going to double the coefficient and then balance the whole thing. And then if that doesn't work, double it again. And then if that doesn't work, double it again. And if that doesn't work, double it again. So what I'm saying is don't do any iterations where you have a 5 or a 7 or something there to balance. So that's typically how we do balancing reactions. Now, if I put this first reaction, I'm going to show you how to do the algebraic technique. So I had AgNO3 plus H2S yields Ag2S plus HNO3. And I'm going to show you how we can use algebra to balance this. In algebra, we know we use letters. So I'm going to use those letters. So what we're going to do is make a series of little algebraic equations. And so over here, I'm going to write my elements. And if you notice, the polyions are staying together. So I'm going to just keep those polyions. And so I'm going to put all those components down. And then I'm going to change the color again. So I have 1A times AG. I have no AG here. Oh, I have 2 AG here. So if I see the arrow, I put an equal sign. And then here's 2 AG on the right side times C. If you look here, 2 times C. And then there's no AG in HNO3. So that's my first reaction. Now my next one, I have NO3. So that's 1 NO3 times A. No NO3 in H2S. I see the arrow. No NO3 in Ag2S. Oh, but I have an NO3 with the D. And there's only one of them. So now I look for H. There's no H in AgNO3. Oh, there's 2 H's. So 2B, arrow is equal. No H's, and there's an H with the HNO3. There's only one of them. And then we look for sulfurs. Nothing in AgNO3. Ooh, there's one with that first guy. Arrow. Oh, there's only one. B equals C. And then there's nothing with HNO3. So what we can do is say A equals 1 to make our life easier, and we're just going to solve them. So if A equals 1, I might go to this reaction next and go, okay, D is 1. And then I can solve over here. If I use this equation, A equals 2C. If A is 1, that means 1/2 is equal to C. So 1/2 would be C. And then if C is 1/2, according to this reaction, the B would be 1/2. Well, we're not going to have fractions in our balanced reactions, so we're going to multiply by a common denominator. My guess is 2 would cancel everything out, making A 2 B1, C1, D2. And so this would be a 2. There would be nothing for the H2S. It's a 1. Nothing for the Ag2S, and then 2 for HNO3. So it's a little bit time consuming, but if you can't get a reaction about, this should work almost every time. And so I thought it would just be useful to add another technique to your toolbox. So I do have lots of practice problems available for you. So you could always look through these. There's also a simulation, and this should help you along with some videos as well.